Shreya Dhara, and this is my Physics 2212 Lab 4 on bar magnets. So to provide an introduction for the purpose of this lab, we compared the distance dependence of the magnetic field with a small bar magnet for on, off, and perpendicular magnetic fields. And then we used the Biot-Savart law in a smartphone magnetometer app for the first half of the lab. For the second half of the lab, we used a glow script model to create a representation of what the magnetic field would look like for an off field. To provide an introduction of the models, so this lab is largely focused on magnetic fields and dipoles. Magnetic fields are created from moving charges, and the largest contribution to magnetic fields comes from electron spin. And the angular momentum of the electrons is represented by the dipole moment, and here we call that mu. So mu equals IA. And then B field, or the magnetic field, can be measured three different ways. It can be measured on axis, perpendicular to the axis, and off the axis. And we have three different formulas for that. So off axis is represented by this one, on axis is right here, and then perp axis is right here. So you can see they're all slightly different. And then this is what the magnetic field of a bar magnet would look like. It goes from the north to the south pole. Okay, so to provide some initial conditions, the system, I'm just going to call it the bar magnet and Earth. The surroundings are none because we included both in the same system. The initial conditions for the experimental setup are the bar magnet, meter stick, and the magnetometer app, and then we also use some tape to figure out where the sensor in the smartphone was. So the results preview, so the n value we found here through our data analysis is negative 3.18. The value of the magnetic dipole, or mu, is 4.68. And then these are the values I got from GlowScript for the B field at 45 degrees from distance d, and that's right here. So here's the experimental setup. So the steps were to set up the magnetometer app, which is on the smartphone right here. We identified where the chip would be placed using the tape method. We found the X component of the magnetic field at 20 meters, or 0.20, 0.70, 0.120, etc. on axis. And then we found, and that was one experiment using the meter sticks and the smartphone. And the second experiment, we found the Y component of the magnetic field, which is perpendicular to the axis. And then finally, we used GlowScript to find the off-axis magnetic field. So here are the data values for part one. And this is basically just the distance, and then Bx, which is the X component of the magnetic field, as the distance from the magnet changes. We then linearized this and graphed it on the plot shown. And then here are the calculations that I used to find n. So basically, we said the magnetic field of the bar equals kr to the n power, where k is the natural log of k is the y component, and then n is the slope of this graph shown here. So using these values, after a little bit of math, I was able to find the n value to be negative 3.18, and then the mu value to be 4.68. So then I went on to my GlowScript code, and for GlowScript, I basically used this mu value that I just calculated, and I set up this function to calculate the dipole B. And then there's some more code that's not shown here that basically created a bunch of different arrows to help with the GlowScript output, which looks like this. So the green arrows show the magnetic field perpendicular to the axis, the orange arrows show the magnetic field on axis, and the cyan arrows show the magnetic field 45 degrees from the axis. And then here is a value of that right down here. So to answer the questions that were asked in this lab, I said as the magnetometer moves closer to the magnet, the measured X component of the magnetic field increases, and that's because of this formula we saw in the beginning where R is the distance, and basically the closer you get, the larger the value of B you will have. And for the what if question, if we hadn't oriented our experiment to compensate for magnetic north and just put it at some random angle, there would have been interfering results with the Earth's magnetic field. Because we compensated for Earth's magnetic field, we were able to align magnetic north of the bar magnet with Earth's magnetic field. And if we hadn't done this, we would have had completely different magnitudes and values. And the last what if question asks, if you stuck two identical magnets together end to end, the magnitudes might change a little bit, but the directions would largely remain the same as modeled by the glow script. And then some sources of error. We had lots of interference from other magnetic fields and devices. We had a lot of precision and measurement errors during data collection. And then the smartphone app itself was very glitchy, and we had to reset our setup a couple times. That's it. Thank you.